Exception handling is simple, but deep understanding of it is required to master writing effective Python code. In this masterclass, I'll get you there, taking you through everything you need to know from the start, step by step. Let's begin. Exceptions can modify the flow of execution and control through your program. They are triggered automatically when errors are encountered, and they can be both triggered and intercepted by your code. There are 4 statements which we'll cover, the first of which has 2 variations. Try except. This catches exceptions either raised by yourself or by Python and allows you to recover from them. Try finally. This allows you to perform cleanup operations whether exceptions are raised or not. Raise. This allows you to trigger exceptions manually in your code. Assert. This is used heavily in testing, and it conditionally triggers an exception in your code. With as, implements context managers and can be used as part of your overall mastery of control flow in your program. Why would we use exceptions? Well, in a large program with multiple steps, functions and parts in general, there is much that can go wrong, and exception handling on encountering an error lets us abandon everything started already in order to jump to and run specific code that handles such a state. Let's say our program, for example, needs to fetch the latest news articles. If the internet connection is broken, we can anticipate this and execute code telling the user to check their internet connection, as opposed to crashing and closing the program without feedback to the user. Let's jump straight to an example before considering the theory behind it. We'll start off by supposing that our very miniature program consists of opening file.txt and assigning it to f. File.txt doesn't exist, so when we run our program, we get an exception, file not found error. You can imagine that Python tries to execute this line of code. Seeing as there's an exception, Python initiates its default exception handling mechanism, which is to halt the program proceeding any further and printing the exception message to terminal. So, when we add to this program by adding line 2, which is a print statement, and here represents the rest of a normal program, we only get the exception and can see that the rest of our program hasn't executed. Wrapping our code in a try statement allows us to provide our own custom exception handling block. Here, we place the assignment to f inside a try statement and dictate our exception handling in 2 stages. 1. We tell Python which exceptions we want to catch, which exceptions we want the code that we're about to write to apply to. Putting except by itself catches all exceptions, although I'll explain shortly why there are better strategies than this when it comes to wanting a blanket catch-all exception handler. 2. We put code indented within this, and this is the code that will be executed if the relevant exception occurs, i.e. if the relevant exception is caught. We'll put parse here purely for educational purposes. In real life, putting this blanket except followed by a parse will make debugging a nightmare, as you'll have little idea why your program has failed if it is anything other than a few lines of trivial code. So what do we have here? We have line 2 that we know will raise a file not found error. We've wrapped it in a custom handler, so the exception will be caught by line 3. Any code within this block will execute, and then execution will resume with line 4. Now, what's a better strategy for building custom exception handlers? Well, one is to make this more specific. By changing except to except followed by the exception we want to catch, and only the exception we want to catch, in this instance file not found error, what happens is that our custom exception handler will only seek out and catch this exception. What's more, the code within except file not found error won't execute for other exceptions which we want to halt our program. All other exceptions will be subject to the default handling mechanism, so this will give output as before. Let's change line 2 to something that raises a different exception. This time our custom exception block won't run, and neither will subsequent code, because our program will be terminated. If we want our custom exception handler to apply to more than one exception, then we can place all of these exceptions in a tuple-like structure as shown. Now earlier I said that when we put a specific exception, then it only applies to that exception and no other. Well, the true story is that it depends on where the exception lies in the exception hierarchy. Here we'll change it to except OS error. The point is that file not found error subclasses from OS error. To generalize, when we put a specific exception on line 3, both that exception and any other exceptions lower down in the hierarchy, in the class hierarchy that is to say, so a subclass or descendant, will also be caught. We'll explore this in more depth when covering user-defined exceptions. For any try statement, we can have any number of except statements covering various exceptions. What about when both a parent and a subclass are included here? Well, Python will take the first except handler to appear, such that anything that comes after it will be ignored. You can look at the MRO, the method resolution order, if you don't have access to the exception hierarchy and want to know what will catch what. Assert can be thought of as a conditional raise statement. It's essentially shorthand for a particular usage of raise. For instance, assert test is shorthand for if dunder debug, if not test, raise assertion error. The debug conditional line is there so that if you run your program with the capital O flag, e.g. python-O program.py, then the assert statements will be ignored. This will be covered fully in a specific unit testing tutorial, as that's where it's most often used. Similarly, even though context managers with as can be considered with exception handling, it's best left dealt with separately, so that we can focus on mastering try, except, else, finally, in addition to raise. The statements in the try block are run first. If exception 1 is raised at any point during the try block, then statements 2 are run. If any of exception 2 or 3 are raised during the try block, then statements 3 are run. The next line is similar, but if exception 4 is raised at any point during the try block, then the instance of exception 4 is assigned to name4, and it's then made available in this except block, whose statements are then run. Except by itself means that if any exception which has not already been caught within the previous except statements, if it's raised during execution of the try block, then the statements within this except block are executed. The else block is run if no exception was raised during execution of the try block. The block under the try header represents the main action. It's the code that you're trying to run and are wrapping within error processing logic. The except clauses define handlers for exceptions raised during the try block. The else clause provides a handler to be run if no exceptions occur. This is most easily understood with examples. So let's take a look at a few more and then tackle a denser, more in-depth explanation of how try statements work. Here, our main action is assigning index 3 of the string spam, i.e. m, to x. No exceptions are raised, so except run is not printed. Recall that the else block runs if no exceptions are encountered in the try block. Therefore, else run is printed. Anything in a finally block is always run, and it acts as a way of ensuring that, for instance, if a file is opened in a try block, that you can close it even if an exception is going to halt your program. So finally run is printed. We continue onwards with our code, and so the top level is run. Let's change things so that we're asking for index 50 of spam. This raises an index error. We've coded our custom handler to catch index errors, therefore the except run is printed. As we encountered an exception, the else block is ignored, finally is always printed. As we caught our exception, and our program didn't halt, we continue with top level run being printed. Let's just remind ourselves of what our first example printed, when line 2 didn't raise an exception. Now let's change it so that line 2 raises an exception, but a different exception to index error, and one that isn't a subclass of index error. We're trying to divide by 0. Our except block won't be run, as it isn't an index error, it's a 0 division error. We have an exception, so else run won't be printed either. Remember, finally as always run, so we have finally run printed. The default exception handling mechanism is run, so our program is halted, and the top level run is not printed as we can't continue execution of our program. The next section is a bit wordy, so feel free to either listen to it again or listen to it after you've covered the subsequent examples in this tutorial. How do try statements work? Well, when a try statement is entered, Python marks the current program context so it can return to it if an exception occurs. The statements nested under the try header are run first. What happens next depends on whether exceptions are raised while the try block statements are running and whether they match those that the try is watching out for. If an exception occurs while the try block statements are running, and the exception matches one of those that's under the except statement names, this is in essence catching an exception. Python will jump back to the try and run the statements under the first except clause that matches the raised exception, after assigning the raised exception object to the variable named after the as keyword in the clause, if present. After the except block runs, control then resumes below the entire try statement, unless the except block itself raises another exception, in which case the process is started again from this point in the code. If an exception occurs while the try block statements are running, but the exception does not match one that the statement names, the exception is propagated up to the next most recently entered try statement that matches the exception. If no such matching try statement can be found and the search reaches the top level of the process, Python kills the program and prints a default error message. If an exception does not occur while the try block statements are running, Python runs the statements under the else line, if present, and control then resumes below the entire try statement. In other words, except clauses catch any matching exceptions that happen while the try block is running, and the else clause runs only if no exceptions happen while the try block runs. Exceptions raised are matched to exceptions named in except clauses by superclass relationships that we'll explore later, and the empty except clause with no exception name matches all or all of the other exceptions. The except clauses are focused exception handlers. They catch exceptions that occur only within the statements in the associated try block. However, as the try block statements can call functions coded elsewhere in a program, the source of an exception may be outside the try statement itself. In fact, a try block might invoke arbitrarily large amounts of program code, including code that may have try statements of its own, which will be searched first when exceptions occur. That is, try statements can nest at runtime. Both built-in exceptions and those defined by the user are identified by class instance objects. This is what is raised and propagated along by exception processing. There are many benefits to basing exceptions on classes and object-oriented programming principles. They can be organized into categories, which has the potential to simplify development of your code over the iterations. When coded as classes, exceptions support future changes and new exceptions can be added in the future, generally not requiring changes in your try statements already coded. They have state information and behavior. Context information and tools can be stored in exception classes, with instances having access to both attached state information and callable methods. They support inheritance. Class-based exceptions can participate in inheritance hierarchies to obtain and customize common behavior. For example, inherited display methods can provide a common look and feel for error messages. Because all exceptions have to inherit ultimately from base exception, they start off with useful defaults for printing and state retention. Class exceptions are matched by superclass relationships. The raised exception matches an except clause if that except clause names the instance's class or any superclass of it. When a try-statement's except clause lists a superclass, it catches any instance of that superclass as well as instances of all its subclasses lower in the hierarchy. The net effect is that class exceptions naturally support the construction of hierarchies. Superclasses become category names, and subclasses become specific types of exceptions within that category. By naming a general exception superclass, an except clause can catch an entire category of exceptions, which any more specific subclass will match. So how does this play out in code? Well, here we've defined an exception called general. It inherits from the exception base class, and beneath this in the hierarchy, we've defined two further custom exception classes, specific 1 and specific 2. They each inherit from general. We go on to define three functions which each follow the same pattern. We create an instance of each of our custom exceptions, and then raise that instance. From line 22 onwards, we iterate through each function, try calling it, and then have an except statement which catches the general exception or, as we've just stated, any exception within that general category, i.e. derived from general. And we can see that our exception handler has caught both the general exception and the two specific exceptions because they are subclasses of general. Our exception handler code, this code block here, calls xinfo, which is a function in the sys built-in module that returns a 3-item tuple providing information on the most recent exception handled. If no exception is being handled, then it returns none, none, none. Otherwise, it tells us the exception type, the exception value, i.e. the particular instance, and the traceback, which encapsulates the call stack at the point where the exception originally occurred. So here we see the memory address. Let's alter things slightly so that we only see the exception type. Now, note that we can capture the exception instance by adding as and then any name we like. In this way, we can write code that we would normally do to ascertain the class of our instance. We can see that the output is identical to before. All built-in exceptions that Python itself may raise are predefined class objects organized in a shallow hierarchy with general superclass categories and specific subclass types. They live as built-in names in the module called built-ins. See how we can raise a type error without calling the class, i.e. without creating an instance ourselves. When we do this, Python calls the constructor without any arguments. So now, when we raise type error having created an instance ourselves, we get an identical output. We've mentioned that exceptions have some default behaviors. Let's explore that in more detail. If we pass in a value into the constructor, that value is then printed as the error message. The values we pass in are contained as a tuple within the args attribute. And it works whether we pass in one, more than one, or no arguments at all. Also, you'll be aware that for user-defined classes, the default wrapper isn't the most visually attractive of wrappers, but as you can see, the default wrapper for exceptions prints out the args attribute. So that's what we mean when we say that exceptions have a set of unique defaults. These are inherited from base exception, which is the topmost root, although it's not meant to be inherited from directly. You should inherit from exception, which is the root of user-defined exceptions and itself inherits immediately from base exception. In the exception hierarchy, exception is a superclass to all of the built-in exceptions apart from the system exit event classes. These include system exit, keyboard interrupt, and generator exit. By following this convention, naming exception in a try-statement's handler ensures that your program catches everything, all exceptions, apart from system exit events, which should normally be allowed to pass. In essence, exception becomes a catch-all that's more accurate than merely providing an empty except by itself. This explains why arguments passed to built-in exception classes show up in error messages. Any constructor arguments are attached to the instance and are displayed when the instance is printed. The same holds true for user-defined exceptions because they inherit the constructor and display methods present in their built-in superclasses. When intercepted in a try statement, the exception instance object gives access to both the original constructor arguments and the display method. To provide a custom display message, you have to redefine dunder str, dunder string. You'll be aware that generally, user-defined classes redefine dunder repr only, but there are a few contexts where str is preferred, and this is one of them. So, if you treat your custom exception classes as regular classes and therefore only overload the repr operator, then this won't make it through to the display because printing will call str instead, as demonstrated here. Our custom message is printed only when we overload str and it's absent when we overload repr. Exception classes also provide storage for extra state information as instance attributes. Raising an exception may cross arbitrary file boundaries. The raise statement that triggers an exception and the try statement that catches it may be in completely different module files, that is, Python files. It's not generally feasible to store extra details in global variables because the try statement might not know which file the globals reside in. Passing extra state information along in the exception itself allows the try statement to access it more reliably. Code in try statements can therefore access the raised instance by listing an extra variable after the as keyword in an exception handler. This provides a natural hook for supplying data and behavior to the except handler. For example, a program that passes data files might signal a formatting error by raising an exception instance that's filled out with extra details about the error, as shown here. In the except clause here, the variable e is assigned a reference to the instance that was generated when the exception was raised. This gives access to the attributes attached to the instance by the custom constructor. We catch our custom error, assign the instance to e, and then run the log error method, which creates a log file containing a specific error message. It's not hard to imagine how this can be expanded to be of great use in your programs. In such a class, methods, like log_error, may also be inherited from superclasses and instance attributes, just like line and file here provide a place to save state information. This gives extra context for use in later method calls. Moreover, exception classes are free to customize and extend any inherited behavior as you would expect in object-oriented programming. Two points. Firstly, the raised instance object is also available generically as the second item in the result tuple of the xinfo function in the sys built-in module. This is a tool, as you'll recall, that returns information about the most recently raised exception. This interface must be used if you do not list an exception name in an except clause, but still need access to the exception that occurred, or to any of its attached state information or methods. Lastly, although our class's log_error method appends a custom message to a log file, it could also generate Python's standard error message with stack trace using tools in the traceback standard library module, which uses traceback objects. And let me quickly demonstrate that for you. Here we import traceback module, and we define a function divide by 0. This takes in a single argument, x, and then attempts to return x divided by 0. So we wrap divide by 0 passing in 5 as the argument, we wrap that in a try statement, and we'll catch exception. Recall that in the built-in exception hierarchy, exception inherits directly from base exception, and exception will catch anything apart from system exit events. So what we won't catch is generator exit, keyboard interrupt, or system exit. We'll catch anything else. And we then use the printx function of the traceback module and as you can see, it prints the traceback to the file traceback.file. How can we design more smartly with exceptions? Well, let's take a look at control flow nesting with exceptions. We've defined two functions here. Func2 raises a type error on account of trying to add together a tuple and a dict. Func1 wraps a call to Func2 in a try handler with a custom exception handler that catches type error and prints inner try block. From line 10 onwards, we're now at the top level of this module, and here we've coded a call to Func1 wrapped again in a very similar try handler. When Func2 triggers the type error exception, there will be two active try statements, the one in Func1 and the one at the top level of the module file. Python picks and runs just the most recent try with a matching except, which in this case is the try inside Func1. Again, the place where an exception winds up jumping to depends on the control flow through the program at runtime. Because of this, to know where you will go, you need to know where you've been. In this case, where exceptions are handled is more a function of control flow than of statement syntax. However, we can also nest exception handlers syntactically. This is where we'll pick up from in the second part of this tutorial.